Hi, we're the University of Florida team, and today we'll be discussing photocatalytic degradation of glyphosate in wastewater streams. Today presenting with us will be me, Gabrielle Bryson, Ryan Winslow, Nico Thomas, Ricker Lampier. We will also have Jack Snyder and Alexandra Rubin as part of our team, but they will not be presenting with us today. An outline of our presentation, we'll start with some background and history of glyphosate usage, transitioning into some problems associated with glyphosate, and then we'll discuss some alternative treatment methods in wastewater systems, transitioning into design recommendations, and then following with a life cycle analysis based on our design recommendation.
For some history, Roundup was first developed by Monsanto in the 1970s for use in agriculture and has become the most widely used herbicide in the United States, if not the world. The primary ingredients of Roundup are glyphosate, as well as polyethyloxylated taloamine, and in more recent years, there's been litigation against Monsanto, which is now Bayer, over the health effects of Roundup exposure.
Some chemical properties of glyphosate include that it's a phosphonic acid, meaning that it is just a coupling of a phosphomethyl group with an amino group, specifically glycine. It has a molecular weight of 169 grams per mole with a very high water solubility of 10 to 12 grams per liter. However, this water solubility is amplified when it becomes a salt, and this is the form used in herbicides. Glyphosate isopropylamine has a water solubility of over 1,000 grams per liter at 25 degrees Celsius room temperature, which can be a problem in terms of water contamination. The two main glyphosate degradation pathways include the carbon-nitrogen cleavage pathway and the carbon-phosphorus cleavage. Carbon-nitrogen initially forms the AMPA and a glyoxylate. The AMPA is a toxic intermediate of glyphosate. It needs to be broken down into phosphate through that carbon-phosphorus bond. Glyoxylate is converted into glycine. Carbon-phosphorus pathway, there are two main forms of degradation mechanisms for glyphosate, abiotic or biotic. For abiotic degradation, we are considering either hydrolysis or photodegradation, hydrolysis being the breakdown upon reaction with water. This is very slow, can take months to years. Photodegradation is breakdown through light exposure. In consideration with natural systems, we're going to be considering sunlight, and this has a negligible degradation of glyphosate in both soil and water systems, especially considering polluted water. Biodegradation is the use of bacteria that can use glyphosate as a source of carbon, phosphorus, or nitrogen. It's very effective, and it's actually the main form of degradation in natural systems, specifically soil systems, but varies conditionally based on oxygen availability, temperature, and pH.
So the mechanism for this herbicide is the disruption of the shikimate pathway, which is an important pathway for plants, bacteria, and fungi for the production of aromatic amino acids. In this, it competitively inhibits the catalysis of the EPSP synthase enzyme, thereby blocking this production, in the end, disrupting metabolic functioning and causing mortality. So for the ecological concerns, you have the species level effects, which include the reproductive, neurogenic, behavioral, and toxic effects, as well as the more system level, you have the shifts in community structure, trophic modification, as well as habitat loss. For the human health effects, you have the major exposure pathways being ingestion, inhalation, and dermal contact. The first of these, ingestion, is the primary exposure route with the highest absorption rate, while inhalation and dermal contact are more occupational, while dermal contact has the lowest absorption rate of all three of these pathways. As for the known human health effects, the one major mechanism by which glyphosate affects human health is it causes dysbiosis, which is the overgrowth of the more opportunistic pathogenic gut bacteria affecting the brain through the gut-brain axis, causing mood dysregulation, Alzheimer's disease, as well as Parkinson's disease. Further effects include carcinogenic effects recognized by the IARC, as well as renal complications recognized by the EPA. For the more unknown and more open-ended looming questions are the long-term, low-level exposure effects of glyphosate and AMPA.
Although glyphosate appears to have low concentrations in the wastewater stream, the greater concern is of AMPA, which is the oxidized form of glyphosate, which actually increases in concentration in the wastewater stream because of the oxidative processes that occur within the wastewater treatment process.
The objective of our project is to determine the design option for these wastewater treatment facilities that will degrade this glyphosate and AMPA to prevent any distribution downstream of the wastewater treatment facility. We will produce a suggestion based on available technology, effluent water quality, construction costs, as well as the sustainability and maintenance of the system. We explored 4 different methods for glyphosate treatment and wastewater systems, starting with the traditional methods of chemical oxidation coming in the form of chlorination, but also can come in the form of ozonation. We also discussed the technology of reverse osmosis, biodegradation via Lyase enzyme containing bacteria, and then photolysis with UVA irradiation that is catalyzed by a photocatalyst.
For chemical oxidation, the carbon-nitrogen pathway is utilized, with the hydrolysis mechanism being the primary degradation mechanism for both chlorination and ozonation. Ozonation yields about a 10% greater degradation potential relative to chlorination. However, both are affected by pH, tending to favor more alkaline water streams. With chlorination, complicated kinetics dictate the overall process with the formation of many intermediates, which also need to be oxidized by chlorine. The primary process of glyphosate is one that tends to favor more acidic solutions. However, degradation of AMPA most notably favors alkaline conditions. All in all, the potential for harmful intermediates, mostly chloramines, are the greatest concern before finally yielding nitrogen gas and nitrate. The residence time for these chloramines, specifically trichloramine, can be over 2,000 hours. For ozonation, the hydrolysis mechanism works by the most electronegative oxygen attacking the amine group, which is the nitrogen in the glyphosate molecule. For both glyphosate and AMPA, deprotonated conditions are favored to increase the efficacy of the oxidation of ozone, since the ozone will react with protons in water to form additional water and hydrogen peroxide. Concerns with ozonation include the maintenance of ideal pH conditions and the overall operation cost of ozone. Reverse osmosis has the potential to remove over 90% of glyphosate and AMPA, and that is because the molecular weight is greater than 150 grams per mole, which is the typical size threshold for membrane filtration. Nanofiltration and ultrafiltration have also been found to be effective. However, high operating cost of replacing these membranes and maintaining pressure, and the removal of essential minerals from the water stream pose as a significant concern in the implementation of reverse osmosis.
For our biodegradation route, we considered CP containing bacteria. These bacteria contain a 14-code genetic pH and operon, which encodes these bacteria with an enzymatic complex that allows these bacteria to break the carbon-phosphorus bonds found in organophosphates. This can be very effective, and these enzymes are contained in 26 of the 133 bacteria found in soil systems, and 24 of these 26 are also capable of degrading AMPA. For wastewater treatment facilities, we would consider just enhancing homologs inside the already existing activated sludge to enhance the bacteria that contain these enzymes and the enzymes themselves to increase the degradation that you will have in that wastewater stream. For our photolysis method, we considered photocatalytic degradation via UVA irradiation, and UVA radiation just being in that 320 to 400 nanometer wavelength, and then exposing this to a catalyst or specifically a metal semiconductor, most typically titanium oxide, but can also come in the form of other metal semiconductors, and this generates a complete or near complete degradation of glyphosate, and this process can be integrated into already existing wastewater facilities. It's a 3-step process which involves an initial dark period in which the photocatalyst is introduced, and then the UV lamps are turned on, in which the degradation actually occurs, and then a final filtration of that photocatalyst out of the wastewater stream. Our personal design recommendation was using this photocatalytic degradation via the UVA irradiation. The main concern, or the first concern that we had, is where are we going to place this in a wastewater treatment facility? And we came to 2 conclusions. One, that this treatment technology had to be following filtration and also had to be prior to chlorination. We want to follow it filtrate from the filtration because of the turbidity and the suspended solids in the wastewater streams, which can reduce the UV transmittance and therefore also the effectiveness of the degradation. And so we want to locate it after the filtration so that we can reduce the majority of the solids content in this water.
The reason for locating prior to chlorination is to add an additional safety factor. In case any residuals of glyphosate or AMPA are not fully degraded in the photolysis process, any residuals will be degraded in the chlorination process, as demonstrated via the chlorination kinetic slide.
Our wastewater treatment, in terms of the design, is going to come in these 3 steps of this introduction of the photocatalyst, and then the degradation with the UV light, and then a final filtration step.
The photocatalyst we decided on was titanium oxide or titanium dioxide, and that is because titanium oxide is the most commonly used photocatalyst because it is particularly stable, has low bioavailability, and strong oxidative power as a UV photocatalyst. Additionally, it is strong as an oxidation agent relative to its cost, thus it has a high value. We considered other metal oxides like iron and aluminum. However, concerns over fouling and toxicity, as well as the potential to react with chlorine, led us not to consider these options. Lastly, we considered concerns with nanoparticles in the effluent, so we decided on using a composite to increase the particle size, yet maintain the degradative potential in the photocatalyst process. We decided on using granular activated carbon because of activated carbon allows for the precise selection of particle size based on the selection of carbons. Additionally, activated carbon has remediative properties, and that is because of the high surface area allowing for absorption onto the carbon surface of other molecules. The titanium oxide activated carbon composite will be prepared using a titanium precursor as a source of titanium, prepared dropwise through the acid mixture of an organic acid and an additional proton source, typically acetic acid and nitric acid, respectively. The use of a strong soluble base is needed to neutralize the acid as a buffer solution. The calcination process occurs at over 500 degrees Celsius for several hours to allow for the titanium oxide to anneal to the activated carbon surface.
And now for the designs of the dark tank, the UV irradiation modules, and the filters. The purpose of the dark tank is to thoroughly mix the photocatalyst until an equilibrium state with the effluent is reached. There will be about 5,060 cubic feet of total treatment volume to work with, and this system is designed to handle a maximum of 6 million gallons per day of inflow. Each unit of inflow will experience a 30-minute residence time within the system. The tank is divided into 3 sections with 1 impeller each for mixing purposes. The UV irradiation modules will work to break down the glyphosate molecules, and each one will have 46 cubic feet of treatment volume. Inside each module, there will be 6 rows of 30 UV bulbs. Each UV bulb will have a 0.8-inch diameter with 1.2-inch gaps in between. This is the overall layout of the UV irradiation modules. It will require 30 chambers laid out in 3 parallel series. Once again, the total treatment time will be 30 minutes. And the purpose of the 3 parallel series is in case one column of the chambers needs to go down for maintenance or cleaning, there will still be 2 columns available for operation. The filters are to remove the photocatalyst substrate from the solution, and they will be designed to reach a target Reynolds number of less than 10, under 6 million gallons per day of inflow. To achieve this, 14 1-foot diameters will need to be installed per module. The median diameter of the granular filtration media will need to be around 1 millimeter, which is that of a coarse sand. The average effective porosity for a coarse sand is between 0.26 and 0.36, so we will assume an average of about 0.31. The kinematic viscosity we will assume to be about 1 × 10⁻⁵ square feet per second, which corresponds to a mean temperature for Gainesville of around 70 degrees Fahrenheit. And when all those numbers are put into the calculation, the resulting filter Reynolds number is about 9.52.
For additional infrastructure that we can add into the system would include a control center, which would just allow you to control which UV lamps are on or which modules are on. Also, the the transmittance that you're getting from those lamps. This is mainly for maintenance. You can also have a crane. This allows you to remove the lamps for replacement or replacement of the ballast. And then you can also integrate grading and handrails, which are just more of a personnel inclusion for safety for moving about these systems. In terms of a life cycle analysis of our system, we are going to start with capital construction costs and then move into operation and maintenance costs on an annual basis.
The site the dark tank and UV modules will be built on will be assumed to be of a sandy subgrade with light grass cover. Before the foundation with strip footings can be installed, some earthwork must be performed. This includes topsoil stripping and stockpiling and trench excavation. Structural backfill and vibratory roller densification will be required as needed if there are any imperfections in grade on site. Lastly, fine machine grading will be used to confirm that the site is level to specification. In total, the earthwork is expected to cost $1,100 plus the price of the as-needed fill. The breakdown for the concrete foundation costs can be found here. This includes the cost for the foundation mat concrete itself, the price of the reinforced strip footings, the wooden foundation forms, the wire fabric reinforcing, concrete placement via direct chute, and bull floating. Similarly, here are the costs for the concrete walls and baffles, which includes the concrete itself, placement of the concrete via pump, and the wooden concrete wall and baffle forms. Additionally, there is a price for the pipe connections between the UV modules, which is also listed here. In total, the concrete is expected to cost about $197,000, which brings our running subtotal to $198,000. Adding to this subtotal, we must include a general administrative requirements at 7%, a sales tax at 6%, a general contractor's overhead and profit rate for materials and equipment of 10%, and a rate for labor at 53.9%. We will apply a contingency factor of 5% in the event of any unforeseen circumstances during construction, a bond at $4,000, and we will adjust the total by 84.2% to adjust to the Gainesville location. This brings the grand total to around $259,000.
For operation and maintenance, our first concern is going to be lamp fouling. It is caused from metal buildup or scale onto these quartz tubes and can be amplified by the turbidity or hardness of the water and the warmth produced by the UV lamps. It may also result from depositions of mineral salts, suspended solids, biofilms, oils, and grease. And so we will have to clean these tubes. And for a 6 million gallon per day treatment facility, which is the one we are considering, the most cost-effective way of cleaning will be manually, with usually a mild acidic solution. Most commonly used in the industry will be citric acid, which will come to about $200 per gallon.
So for the photocatalyst, we need approximately 5 grams per liter of this titanium oxide. And for our 6 million gallons per day design, we'll need approximately 110,000 kilograms of this catalyst. We are quoted for a ton of this catalyst at about $3,350 by Industrial Minerals. As for the component replacements, the lifetime of these bulbs is nearly a year, and the average cost per bulb is $185. The amount of bulbs we'll need for the system is 4,140, so thus annually the entire cost for installation and replacement is about $766,000. For the lamp valves, they need to be replaced every 10 years, and a replacement costs roughly $30. As for the filtration replacement, this is more site-specific, so we'll not include this. For the labor costs, we have the operation calibration of the system, as well as the maintenance of the quartz sleeve, and the quality assurance and quality control testing. The labor costs are incurred on a plant-wide basis generally, and they depend a lot on the local labor market. But for a plant of similar complexity and design, we can estimate this cost to be approximately $50,000 per year. For the quality assurance and quality control testing, on the one hand, you have the EPA mandated testing, which uses the EPA method 547, high performance liquid chromatography. But we recommend further testing for the quality assurance and quality control of our design. So we would recommend using these diffuse reflective spectroscopy as a cheaper, more inexpensive, and quick method using spot tests on paper. The initial equipment cost for this DRS is $12,000, Well, the sampling cost per 100, which captured the entire variability of the waste stream, will be $15,000.
So our recommendation will be using this UVA irradiation catalyzed with a titanium oxide activated carbon composite. And we'll do this through installing a dark tank and UVA irradiation models, placing it downstream of filtration and upstream of chlorination, with a total cost of about $250K for construction and about $1 million for annual operation and maintenance.